welcome to our tutorial Introduction to Agent-Based Modeling for the IPSS. In this tutorial, you will learn about agent-based modeling using the Agents.jl library for the Julia language. And in this first video, you will hear about what agent-based modeling is, how it is typically used, and we will see first trials in how to get it running in Julia. So why do we need agent-based modeling? Agent-based modeling is a method that's typically used when we want to understand complex systems. Complex systems meaning that we have lots of parts that are independently moving, so to say, in the system, and there are strong interdependencies between these parts. It's not necessary that the individual behaviors or rules are complicated, but just in taking all the parts together, which are lots of them and lots of interactions happening, this introduces complexity by making the overall behavior hard to predict. And there's a very interesting example that has been used a lot to explain how agent-based modeling can be useful, namely so-called flocking behavior. Flocking behavior here seen by starlings is a behavior where the whole flock behaves as if it were a tightly coherent agent that has a plan or a strategy of what to do, while we know that in reality there is no orchestrator of this movement. It's only the individual birds having individual localized rules, namely stay in the center of the swarm, try not to be on the outside of it, don't hit the next bird, so try to stay in line with them. And when we're adding these rules on individual levels and having a multitude of these, we see this very interesting flocking behavior that on a higher scale, namely on the flock scale, looks like it has been orchestrated. And this sentence, the whole is greater than the sum of its parts, is kind of the essence of what we would call emergence. And emergence is a central phenomenon that we look into when we understand individual behavior of agents, and when it's easy to put into a model, we can then put lots of these individuals into a simulation, and then we can witness the emergence of more complex behavior or more intricate behavior on a higher scale. And a method, especially a digital method that we use to do this, to simulate these behaviors, is agent-based modeling. So what exactly is agent-based modeling? Agent-based models typically have two components. There is an agent and there is an environment. And in the case mentioned before, we have the birds, which are the agents, and they fly in front of the sky, which is their environment, but also the other agents are part of the environment. So by simulating the individual behavior of a single bird, we can then try to see what individual behavior constitutes this macroscopic behavior and that we see in witnessing the whole flock. We can also use this in other scenarios. For example, if we want to understand how traffic works, we can put cars as agents or individuals in cars as agents, and we can put them in front of or on top of roads, and we can make them utilize electrical energy from the grid if they're electronic cars, and we can make prices dependent on sunlight availability and so on. So we can use them to understand the coupling of weather and availability of electric vehicles, for example. But what we're most interested in is how people interact with one another. So people would be the individual agents, and they can have different types of environments. They could be using social media, so an online social network, which would be their environment, obviously including all the other agents in there. But also a virus could be part of the environment. So epidemiological simulations would have maybe a virus outbreak, and the agents would be transmitting the virus, which would be part of the environment. So why do we even use a tool like agent-based modeling? We'll still see what that even means. Why not other types of models? So another typical type of model that you might see is an equation-based model. And in this case, it's U equals R times I. So that's voltage equals resistance times current. And the idea here is that we have a law that determines using the components in electricity, the resistance and the current, to determine the voltage. And the reason why we can use this formula, even if we know that under the hood there's lots of atoms, lots of electrons happening here, is because we assume that all the electrons that play a role here are basically the same. There is no heterogeneity. It's a very homogeneous group of things that we want to model, so we can collect them in a variable or in a compartment. And we can do this for epidemiological models as well, where we assume that every person is equal, or we have different compartments of similar people. And then we can use equation-based models as well to do predicting of outbreaks, for example. But whenever we are interested in the heterogeneity of people, and obviously we might be interested in that, agent-based models have a very strong part to play, especially because we can pick out the individual agent and investigate what has happened to that person during the simulation. This has unique, powerful abilities where we can try to understand specific trajectories of individuals inside of a simulation. So let's take one very basic example, which we often use to demonstrate the strength of agent-based modeling. And this example is a game that we can play. And the first game that we play, or the first task that we play, is the coward task. And the idea is you can actually play that in real life. You can have some of your friends with you or other students with you. And the idea is every person picks one enemy and picks one friend. And in the coward game, your goal is to put your friend between your enemy and you, so that your friend shields you away from your enemy. And this is a very basic rule. It's just saying put that try to go somewhere that the other agent is in between you and that enemy agent. But it's really hard to determine what is going to happen. So what do you think that might happen? What would happen on the global scale if this is what people would be doing? And if you're able to predict what is really happening, then this tells you that you have a very good understanding of how spatial rules might play out. But it could also be luck. It's really hard to do this in general. This is a basic example. So hold your thought on what you think might happen while we put on the second game. The second game is the hero game. And in this task, your goal is to put yourself between your friend and your enemy. So in this case, you kind of like are the superhero who shields your friend from your enemy. Interestingly, your friend will pick a different friend and a different enemy. So friendship in this case does not have to be mutual. It can go different ways, as in reality, you can assume someone is your friend and they might not assume that you're their friend. Similarly, for being enemies, the enemy relationship is also not symmetrical in this case. So your enemy does not think that you are their enemy, not necessarily at least. And once again, think about what is going to happen if everyone is playing this game, picking two different random people from a group and trying to put themselves in between their friend and their enemy. Try to keep that in mind while we put on the third game, which is even harder. It's the coward or hero game. And in this task, the central idea is, now that you've understood the first two games, to pick yourself secretly a variant to explore. So every agent randomly picks a strategy, either being a coward or a hero, and then picking a specific enemy or a specific friend to play their role of either being a coward or being a hero. And in this type of model, we do have some heterogeneity. So we have cowards and heroes, and everyone has an individual enemy and an individual friend. And that is something that is really hard to do in a equation-based model. What do you think is the outcome of this rule? Does it depend on who picks whom? Does it depend on the amount of cowards or on the amount of heroes? We assume that we have 50% cowards and 50% heroes, and we will now see the results of all three games. On the left, we have the cowards game, and sadly this starts the latest. And what will happen is everyone will try to go as far as possible from their enemy and trying to put their friend in between them. And in many instances, you will see the behavior to the left. Everyone go to the furthest possible location in the room, this way cornering them to the walls. The heroes game is interesting because everyone will try to move in between their friend and enemy, and since everyone is someone's friend or someone's enemy, in at least in most cases, randomly it could occur differently, all the agents will move to the center of the screen. And if you conduct this experiment in reality, you will see that the people will cluster together in their most comfortable distance. So depending on where you're conducting this experiment, you will have a very tight or even more loosely coupled cluster. The most interesting results is the one where we have these mixed strategies, cowards or heroes, and currently we're watching a game or a version of this simulation where there is no stable state, since everyone is forcing someone else to move somewhere. There can also be this state, which we see right now, where everyone is aligning in a way, and then we kind of reach a stable state where everyone found their position. And in contrast, this version is one where we do not find a stable state. And this is really hard to determine. What can you ahead of time determine whether you reach a stable state or not? And it depends on the individual selections of the agents, who is their friend and who is the enemy, and also which strategy they apply. Because obviously, depending on how many people pick a coward and how many people pick a hero, there are all different versions possible, from the pure coward game to the pure hero game, but also these different strategies in a mixed game. So it's really hard to predict from the rules alone what will happen, but it also depends on the initial conditions of this game. And that is a feature that we often see in agent-based modeling, that it is not only important that we understand the rules and how they play out, but also the conditions in which these rules apply. And for that reason, in agent-based modeling, what we're seeing here is agent-based modeling, by the way, using the NetLogo language, is that it plays a large role in which condition we start. Thus, it makes sense to run simulations multiple times with different initial conditions to understand if the outcomes that we see are an outcome of the rules that we put into the model, or of the initial conditions that we put into the model. And this is our first video for agent-based modeling, and in the next video we'll see how we translate all this to Julia.